So my talk today will be about novelty and what does this term means for the task of question answering. Specifically, I will introduce a deep learning approach for ranking answers to a question and a dedicated novelty-aware training schema. Okay, let's start with an example. What are the top places to visit in New York? This situation is probably familiar to you. I know that when I'm visiting a new city for the first time, I'm searching for a similar question and finding myself navigating to a similar community question answering site. Now, what do we want to see at top rankings for such a question? There are many aspects about the question that can be considered, right? For example, some will be interested in museums. Others might be interested in Broadway, in culinary, or in many other things. Given so many aspects to consider about the question, I know I don't want to read answer after answer after answer and say approximately the same with only some different word. To see a wider view about the question, I want to read as much views the user gave as possible within the first few answers. Okay, this example brings us to intuitively define our goal as exposing the users of the community question answering site to a diversified list of results. Okay, in other words, we want to provide ranking over answers in a way that this ranking will promote answers on both the relevance to the question and by the amount of novelty they introduce with respect to other answers chosen so far. Now, this is with distinction to older approaches where you can see in many community question answering sites that all first answers are similar, talking about the same, but they are seemingly good. Of course, they are if the algorithm chose it to be good and there is another similar, if it doesn't take into account the former answer, so it might be similar. Okay, to do this, first we argue for the need to express relationships over triplet. A triplet is a question and two answers. In this way, we can cover relationships like this is a good answer to the question and diverse with respect to the second answer of the triplet. Okay? Second, we want to make use of the large masses of unlabeled data found on the web to train a scoring function and train it in a way that will promote answer based on the relevance to the question and based on the amount of marginal novelty. Okay, let's start with the network topology. The network topology is over triplet, a question and two answers. We first transform each word in each sentence to its vector representation. The next layer is an LSTM encoder. We process each word sequentially to get at the end the fixed size representation for each sentence, which could be an answer or a question. We then feed it to a layer we call triplet tensor layer. A tensor is a multidimensional parameters object we use to interact between the two representations. And the final layer is a feed-forward scoring layer, able to produce a score on that triplet. Now, usually training such network will require large amounts of labeled data. One of our goals is to make use of the unlabeled data and to make the right assumptions in order to create labels to train in our way, in a novel way. We do this with a process we call Novelty-Driven Sampling. We want to present the network with both positive and negative examples. A positive example is a triplet of question, relevant answer to the question, and the novel answer with respect to the other answer in the triplet. A negative example is one of two types: a negative novelty, which is a question, a relevant answer to it, and where the second answer is not novel, is similar to the other answer, and a negative type 2 is negative relevance, where the triplet is a question, a random answer chosen to another question, and an answer that is diverse with respect to it. Okay, so to sample relevant answer, we don't really know it from the data set. We need to make assumptions. So the assumption we make for a relevant answer is that the answer with the most votes, it's the most thumbs up in the Yahoo Answers dataset, is relevant. This is a reasonable assumption given many users gave this thumbs up. Now, to measure the amount of similarity or diversity between two answers, we are doing the following. We first represent each of the answers with a vector representation. The vector representation can be one of the following, can be latent Dirichlet allocation or LSTM. We then compute the cosine similarity between the representations, okay? We choose the top cosine similarities to be similar answers and the bottom to be diverse answers. Now for this step, incorporating more than one representation for the answer can make sense because it will introduce the network with various aspects of novelty. For example, if it's an LDA, it's more topical sense of novelty. An LSTM depends on the objective, but more semantical view, etc. Okay, once we have our training data with labels, we are optimizing on the max margin criterion, on the margin between a score of a positive example and the score of the negative examples. Intuitively, this should bring us to a point in space where the scores of the what we called good example will be separated by some margin in space from the bad examples. Once we train the scoring function, our greedy ranking algorithm is quite intuitive. For a question with n answers, we compute an n by n scores matrix correspond to the question with every combination of two of its answers. And then the next answer selection step, select the next answer to be the answer with the highest sum of scores with respect to the question and all the answers chosen so far. So this next answer should be relevant to the question and also introduce novelty with respect to the set of answers we've chosen so far. And at each step, we look at this whole set so we don't miss any information on the way. We measure the performance of our algorithm on two gold standard data sets. Our evaluation metric named alpha and DCG. This metric rewards answers with the highest number of aspects. It's a discounted one. If you said this aspect exists lower in ranking, you'll get less. We can see our method outperforms all unsupervised method on both data sets and is able to compete with the state-of-the-art supervised method on the same gold standard. Now here is one example question I took from the gold standard. 8 relevant aspects appear in 10 answers provided for this question. You can see the aspects colored the same across answers. Our algorithm is able to cover all 8 aspects within the first 4 answers, which means there are 6 more answers after that that doesn't introduce any novelty as a human labor gave. And so searching for some deeper understanding of the novelty feature this network is learning, we have expected the LSTM representations for a sentence, for an answer, to express these features. And so we've projected the answer's LSTM representations into the 3 most informative dimensions. Each dot in space is an answer, annotated with the list of the aspects it contained from the human label dataset. Observing this, we can see a large gap between answers contain high number of aspects and answers contain low number of aspects. Moreover, observing the aspects behavior across answers, we can see that answers contain similar aspects tend to be nearby in space. For example, the answers contains only the aspects 4 are clustered together, while answers with aspects 5 or 2 are further. Similar phenomenon happens on the right side when we are thinking about aspects intersection. So we can see the behavior of the network by visualizing the hidden layers. Okay, to conclude, we have motivated the importance of novelty for the task of question answering. We've proposed a deep learning approach to model interactions of a triplet aimed at this task. And to train the network with novelty awareness, we've suggested a dedicated training scheme that is able to express novelty and its training step. Thank you.